Hello, and welcome to matrix multiplication. The product, right, the result of multiplication, the product of two matrices in general, for matrices A and B, we can take the product AB only if the number of columns of A equals the number of rows of B. Because we multiply the rows of A by the columns of B. The product AB is then obtained by taking its ijth entry to be ABij is from row I of column A, and we're going to multiply that by column J of B. Here we go. Fact, if the dimensions of A are m by n and the dimensions of B are n by k, then the result has dimensions m by k. Okay, so this whole blah blah blah, this whole blah 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 fact, add these two together. What it says is the number of columns of A. This is the columns of A, right? And the rows of B, the second one, A, B, in order. Multiplication in this case has to be in order. B has n rows. So if these two match up, we're okay to multiply. That's at you. Okay to multiply. The result of that multiplication is the other two that may or may not match, right? As long as the ends in the middle match, we're good and we can multiply. This is going to be our result. Okay, so special case, a row matrix multiplied by a column matrix will always have an answer, the form 1 by 1. They still have to match. The link still, it has to be like a 1 by 3 and a 3 by 1, or a 3 by 1 and a 1 by 3. You know, they have to match up so things actually multiply. Let's take a look. We're going to multiply if possible. So I have a matrix A here that's 4, 0, negative 1. It's one row, 3 columns. The second matrix, I take them in order, has negative 4, second row is 1, third row is 8. Notice that it has 3 rows, 1 column, so we'll have a 1 by 3 multiplied by a 3 by 3. That tells me it's okay to multiply, and my result is a 1 by 1 matrix. Let's take a look. So we'll take row 1, multiply it by column 1. So I'll multiply 4 times negative 4. The first entries. The second entry is 0 times 1. Third entry is negative 1 times 8. So 4 times negative 4 is a negative 16. 0 times 1 is 0. Negative 1 times 8 is a negative 8. And negative 16 plus 0 minus 8 is a negative 24. So when I multiply, I end up with just a constant, a 1 by 1 matrix, negative 24, and we could absolutely, that's a 4. My pen just likes to make cross marks. Negative 24, we could put it in a matrix, but frequently when we have an answer of a form 1 by 1, it's just a real number. It's just we just call it negative 24. Here in example 2, we have a let me see. First row is 3, 2, so that's one row, 2 columns. Second matrix is 1, negative 2, which is also one row, 2 columns. 1 by 2 and a 1 by 2. Since the 2 in the middle do not match, we cannot multiply. So we say this does not exist, cannot multiply. Whatever WebAssign tells you, make sure you use those words and probably the case, just in uppercase, lowercase, just to be sure. All right. Third example. Now we're actually going to do some multiplying here. We'll have 0, 1, negative 1, 2. That's a 1 row, 4 column matrix. Multiplied by 1, negative 2, 1. Second row, 0, 1, 3. Third row, 6, 0, 2. And fourth row, negative 1, negative 2, 11. Now as I was calling out that matrix, we saw that it had 4 rows, and we see the 3 columns. Because the 4's in the middle match, we're good to multiply, and we know our result will be a 1 by 3 matrix. 1 by 3 matrix. Okay, so I only have one row, and I'm going to lay it on top of the first column, and I'm going to multiply. So I'll have 0 times 1, 1 times 0, negative 1 times 6, and 2 times negative 1. So I'm going to find those values. That's 0 times 1 is 0, 0 times 1 is still 0. We'll have a negative 6, and a negative 2 makes a negative 8. So from row 1, column 1, I'm going to write that right here. Multiplying row 1 times column 1, my answer goes in row 1, column 1. Using row 1, column 2, all right, so I'm going to call that exactly what it is, row 1, column 2. I'll multiply 0 times negative 2, 1 times 1, negative 1 times 0, and 2 times negative 2. As we see written out here in, let's call that magenta, we'll have 0 plus 1 plus 0 minus 4. So 1 minus 4 is a negative 3. And we see the negative 3 here in row 1, column 2. What we're using to multiply tells us exactly where to put our term. Row 1 times column 3 here in green. We'll have 0 times 1, 1 times 3, negative 1 times 2, and 2 times 11. 0, 3 minus 2 is a 1. 1 plus 22 makes 23. We multiplied row 1 times column 3, and our answer went right here in row 1, column 3. All right, so when we multiply, we're taking a full row, multiplying it by a full column, getting a single value, and putting it in row column. All right, let's move on. If you wanted to multiply these on Excel, I put this in just one table. I'll show you in a later example. I'll give you a better example of how I did this. So I put in, this is A1, A2, A3, A4. And then I put in my two matrices, and then I multiplied them, and I got my same answer here that we just had. Oops, scroll back. Negative 8, negative 3, 23. All right, so Excel can do this for you. And I'm all about technology. There's also a matrix multiplier calculator that I put access to in the Chapter 5 folder. If you want to use it for your multiplication needs. But for now, I'm going to show you the steps so you know what's going on. You can do it by hand, and once you get comfortable, that's when you should just use the calculator to do the rest. But make sure you understand the process first. Problem number 4. Okay, so this is confirming example 3 with Excel. Fantastic. Example 4, we'll have 0, 1, 1, 0, 0, 1, pause, 1, 0. So it's a 2 by 2 matrix multiplied by the matrix 3, negative 3. Next row, 2, negative 1. Also a 2 by 2. Since the 2's in the middle match, we know we can multiply. The 2's on the outside tell us we're going to have a 2 by 2 matrix. And here, instead of doing it off to the side, I did it inside the matrix itself. So this is row 1, column 1 of our answer. So we'll take row 1 and we'll multiply by column 1. 0 times 3, 1 times 2. 0 times 3, 1 times 2. That's 0 plus 2, which is a 2. Now I'll use row 1, column 2. 0 times negative 3, 1 times negative 1. Right? What did I multiply? Row 1 times column 2. Where did it go? It ended up right there in row 1, column 2 in the matrix. I get negative 1. Fantastic. We keep going. Now that we've finished, we know it's a 2 by 2. We already have 2 columns in row 1. Now we can move to row 2, column 1. And I'll multiply 1 times 3, 0 times 2. That's 3 plus 0, which is 3. And then finally, I'll multiply row 2 times column 2. 1 times negative 3, 0 times negative 1. I'll end up with a negative 3 in row 2, column 2. That's my answer matrix. These are my instructions on how to find each of those numbers. And it tells me my answer goes in row 1, column 1. I must have multiplied row 1 times column 1. My answer's in row 2, column 2. I must have multiplied row 2 by column 2. All right. Fantastic. Now, there's a special matrix that's going to do a lot for us, and it's called the identity matrix. And you probably saw this in Math for the Social Sciences 1 here at UTEP. We call that Math 1320. But we use calculators when we did matrices in 1320, and that's why I encourage you to use them now too. The identity matrix, the n by n, notice they match. They are both n's. All right, so same dimensions. This is a square matrix because the rows and columns match. The n by n identity matrix I is the matrix with ones down the diagonal and zeros everywhere else. That is capital I of II equals 1, and capital I of ij, where I does not equal j, is 0. So I would call this an I2. It's an identity matrix that is square with 2 rows, 2 columns. And I would call this I3. It is a square matrix, 3 by 3, 3 rows, 3 columns. Identity, ones along the diagonal, zeros elsewhere. And it could get bigger, definitely gets bigger. So some properties of matrix addition and multiplication. We already talked about the addition ones. Addition, if we add the 0, we get zeros. This is our only new, right, from here down. These were in all 5.1. I've already talked about those. Check out the video for matrix addition and scalar multiplication if you'd like to know more. But let's talk specifically about the multiplicative properties. If we're going to multiply 3 matrices in this order, A times B times C, I can either multiply AB and then take that result and multiply it by C, or I can multiply BC and take A and multiply by that result. In this order, always in order. All right, it is not true that AB is equal to BA. That is not true. So we can't switch up the order of multiplication when it comes to matrices, and we'll see some examples of that eventually. But for right now, just keep in mind, we cannot switch the order of multiplication in matrices. Okay, associative law. If I'm multiplying 2 matrices AB by a scalar, I can multiply the scalar by one of them first and then multiply. If I have 2 scalars that I'm multiplying, I can multiply one scalar times A and then the other, or I can multiply the scalars and then multiply by the matrix. The identity matrix is like multiplying by 1, either side. The identity, we could switch them up. That's all cool. Distributive law. If you're multiplying a matrix A times a sum B plus C, then you can multiply A times B and then A times C in that order. If you're multiplying a sum by a matrix C, then you can multiply A times C and B times C. Notice the order is preserved. And multiplication by the 0 matrix. If we multiply the 0 matrix times any matrix A on either side, we get 0. And that 0 is the matrix. I'm going to call it 0 bar. It's the matrix with all zeros. Regardless of what size it is, it just has zeros. With transpositions, we talked a little bit about the sum. The transposition of a sum is the sum of the transpositions. Transposition of a scalar, we could take the scalar first or do the scalar last after transposition. It doesn't matter. This is our new one. If we have AB transpose, when we multiply, if we want to do the transpose first, notice that the order changes. Pay attention to the order. I can't read that either, so let me write it better. All right, the order switches up if we do transposes first and then multiply. All right, now why do we care? Why do we need to multiply these? We're going to use them for systems of equations. For a system of equations, we can write matrices as the form A times X equals B, where A is a matrix consisting of all the coefficients of all the variables, X is the variable column matrix, and B is the result matrix. Similarly, we can transform AX equals B into a system of equations. So I'm going to rewrite in the opposite form here. Here we have a matrix system AX equals B. What I'm going to do really is I'm going to take row 1 of matrix A and multiply it by column 1 of matrix X. Notice this is a 3 by 3. And what is our variable matrix? Our X matrix has 3 rows and 1 column. This tells us it's okay to multiply. My answer is going to be a 3 by 1. Cool. So 1 times X, negative 1 times Y, 4 times Z equals negative 3. Negative 1/3 X minus 3Y plus 1/3 Z equals negative 1. And 3 times X plus 0 times Y plus 1 times Z equals 2. It's up to you whether or not you write that 0Y. I write it just so we could see that it doesn't, quote, disappear. But we can get lazy and not deal with it later, right? Like I would probably, if I were solving this by hand, I would eliminate Y from these two equations. Wow, math hard, language harder. I would eliminate Y from these two equations, and then you'll have an equation in X and Z, and these two would simplify to an equation in X and Z, and you can solve from there. But we're not asked to solve, so we're not going to do that right now. We write in the opposite form. Here's a matrix equation that we wrote as a system. Now we're going to take this system apart and write it as a matrix equation. So what are my coefficients? My coefficients are 1, 1, 2. 1, 1, 2. Second equation, 4, 2, negative 1. 4, 2, negative 1. So the matrix takes all these coefficients and says, hey, we don't need variables because we have columns. Notice all the X's are lined up, the Y's are lined up, the Z's are lined up, the equal signs are lined up. Everything's all lined up, so why call it X, Y, and Z when I could write the matrix like this and I could deal with things that I don't have to keep track of, is it a Z or is it a 2? Third one, X over 2, notice that X over 2 is the same as 1/2 X, minus Y over the 3 is the same as 1/3 Y. I have nothing written here because there are 0 Z's. So I'm going to take the coefficients 1/2 and negative 1/3 and a 0 because I always have to fill in my matrix. Every row has to have every column filled in. So that's my matrix A. That's all the coefficients. What are my variables? X, Y, Z, X, Y, Z, X, Y, Z. So X, Y, Z, my column matrix of variables. And my answer is over here on the right-hand side, negative 2, negative 8, 4. Now, for now, we're not going to do anything with it. That comes in the next section. All right, but let's talk about an example or two. The U.S. per capita consumption of yogurt and ice cream in 2000 and 2015 was as follows. Per capita, so in 2000, each person ate 6.5 pounds of yogurt, U.S., and 16.1 pounds of ice cream for the entire year. In 2015, we were eating more yogurt than ice cream, 14.4 versus 12.9. All right, we've seen these two thing tables frequently. If we think of this as a 2 by 2 matrix, right, where the rows are yogurt and ice cream and the columns are the years, we can compute the product negative 1, 1, a row matrix, times P. What does it represent? Well, what are we, first of all, negative 1, 1 is a 1 by 2 matrix. Here, P is a 2 by 2 matrix because the 2 by 2s are in the inside. We know that it's okay to multiply. And our result will be a 1 by 2. So we'll have row 1, column 1, row 1, column 2. All row 1, column 2. So what are we doing? We're taking negative 1 times 6.5 and 1 times 16.1. That's row 1 times column 1. Lands us right here in row 1, column 1. But this is the pounds of ice cream minus the pounds of yogurt. So the 9.6 says per capita In the U.S., a 9.6 pounds, 9.6 pounds more ice cream than yogurt in the year 2000. Per capita, U.S. ate 9.6 pounds. Yeah. Now we'll take row 1 times column 2. We'll put our answer in row 1, column 2. We'll take negative 1 times 14.4, positive 1 times 12.9, and we'll say negative 1 times 14.4. This is, again, pounds of ice cream minus the pounds of yogurt, and this is, we actually ate 1.5 pounds less ice cream than yogurt in 2015. There's a 1 in there somewhere. Let me make it stick out. All right, so knowing what the answer is telling you is guided by what it is that you're actually doing. You're subtracting, right? These are all in 2000. I'm comparing my 2000 values. And I'm taking the ice cream and then negative yogurt to see what happens. All right. Next example, the following table shows the number of foreclosures in 3 states during the 3 months of 2011. California, Florida, and Texas. Let's go big, but there's not enough people in Alaska to go bigger. Your law firm handled 10% of all the foreclosures in California, 5% of all the foreclosures in Florida, and 20% of all foreclosures in Texas. We're going to use matrix multiplication to compute the total number of foreclosures handled by your firm in each of the months shown. Okay, so we're going to turn this into a 3x3 matrix. Our rows are California, Florida, Texas. Our rows of one matrix need to match up the columns of another. Notice I handled 10%. I didn't. You did. 10% of all foreclosures in California, 5% in Florida, and 20% in Texas. Here are my rows, so when I multiply, those have to be my columns because we multiply rows times columns, rows times columns. So this is a 1x3. I'll be multiplying it by a 3x3, so my answer will be a 1x3. Now, I could do this by hand, but I'm looking at those numbers and decimals, and I don't want to. So here's how I typed it into Excel. I let Excel do it for me. I'm not even using some fancy online calculator. I'm using something that you all have access to because you're UTEP students. Or as students of whatever school, you probably have Office 365. So I take 10%, 5%, 20%. I didn't add the extra zeros as they weren't needed. And then I put in my, let's scroll up here so we can see our June is in column D, July is in column E, and August is in column F. Make sure I put the numbers in correctly. That's usually the biggest issue. And then to get the answer, my answer matrix here, I used here, wherever I want my answer to be, I decided my answer was going to be an A4 because nobody used row 4. I wrote the equation equals M mult matrix multiply. My first matrix starts at A1 and goes to C1, comma, my second matrix starts at D1 and goes through F3. All right, so starts here and it will assume D through F, 1 through 3. Hit enter, and I pop up with these answers. But what are those answers? These are California, Florida, and Texas. These answers are now June, July, and August. We handled 8,460 cases in June, 8,860 cases in July, and 9,140 cases in August. Work smart, because you don't always have to work hard. All right, use Excel. Use, if you know how to multiply matrices on your TI graphing calculator, that's awesome. If you know of any other calculator methods that you could use to multiply this is just one. All right, use what makes sense to you, and let me know if you have any questions on the homework.